name's Carly. I'm going to be talking to you about my thesis, which had the goal of determining if there are neural indicators of disfluent speech prior to speaking. So before I get into my current study, I want to give you some background. Speech output requires integrated communication between the auditory, somatosensory, and motor areas. And these areas of the brain communicate via different mechanisms. The feedback mechanism is from the sensory to the motor areas, and the feed-forward mechanism is from the motor to the sensory areas. And disruptions in the communication of this network can lead to maladaptive behaviors such as stuttering. And we are mostly interested in the model of speech production because 90% of stuttering occurrences happen on that first utterance, meaning that there's probably something going on before we even open our mouths. So our current study, as I mentioned, we're trying to determine the differences in neural activity of a stuttering individual's fluent versus stuttering speech. And why it's important? Because stuttering is a very heterogeneous disorder, meaning that there may be different things going on in the person's brain that may not be going on in different stuttering individuals' brains. And so by understanding one individual's neural activity, we can maybe understand what's happening and improve speech therapies with neurological technologies. So we have 3 adult male stutterers in this experiment, and I know it seems like a few number, but we're doing a trial-by-trial analysis. So we're not trying to generalize our data. We're really looking on an individual basis, and analysis is only going to be per each individual. And how we're going to get our data is with electroencephalography, which I'm going to get into in the next slide. And so how we get, what they're going to be doing is they're going to have a cued speaking condition followed by separation of these conditions and the data based on if they stuttered on that word or if they spoke the word fluently. And that's what I mean by a trial-by-trial analysis, because we're going to be looking at each trial as a data point in my ANOVA study, which is how we're going to see if these differences are significant. So the primary thing that we're looking for is this difference in the brain signal, is there a difference in the trial type, fluent versus disfluent? But we're also looking at interactions of location and lateralization, meaning is the signal stronger in the frontal areas or in the left versus the right hemisphere? And if you know anything about the brain, your functions are kind of mapped in different areas, so this can help us kind of understand what's going on more if there's some topographic effects. And so how I'm getting my data is with this paradigm. And so we have 4 different conditions with 2 main goals. The first goal is to see is stuttering word specific. So how we're doing that is we're having the word go condition, which is seen in A and B. And in this condition, they can prepare their speech, because they know the word 1500 milliseconds before they have to say it. So this is kind of an unrealistic speech pattern, because we normally don't know what we're going to say 1.5 seconds before we're going to say it. So we have our cue word condition, which is a little bit more realistic, induces more stress in hopes of seeing more stuttering trials, and that's seen in C and D. The second thing that we're trying to accomplish with this experimental design is probing the auditory cortex, because previous experiments have found some correlations between auditory cortex sensitivity and stuttering, and I'm going to get into that as well. And then so we have our non-auditory trials without the little speaker to serve as that control. So as I mentioned, I'm going to talk about electroencephalography. And so what this is the subject puts on a cap with 64 electrodes that will pick up your neural activity all throughout the scalp. And it has great temporal, meaning time, so you can see activity in real time, and good spatial resolution as well. And so this auditory cortex sensitivity that I was talking about, that's mainly going to be of interest when we're looking at our event-related potential, because with that auditory cue, we're going to get this phase-locked peaks that we see. And what I'm primarily interested in, this is my real data from one of the subjects, is this big difference between the fluent and disfluent trials here, as well as here. So that's 50 milliseconds after the cue and 200 milliseconds after hearing that auditory probe. And our second one is looks at the changes over time. And so on the y-axis we have frequencies. So brain activity oscillates at different frequencies. And so the alpha, which is 8 to 12 hertz, and the beta, which is 13 to 24 hertz. So that beta is the red and alpha is the black box. Those are where we saw in previous experiments major differences between the fluid and the dysfluidic. So the strength of that signal is represented by the intensity of the color. And a darker blue is a decrease, and then the warmer colors are increase in that signal. So I'm going to go by each subject because there's only 3. And our first subject was the only subject to have significant results with this auditory word go Q and the auditory ERP. So you can see over there, you see big differences between the trials in the P50 and the positive the P200. And then these graphs here just show it over across all the electrodes in the brain. And we only chose 6 electrodes because we didn't need to see the whole network. We just wanted a spatially distinct choice. But you can see we have the best success in the frontal electrodes for this subject. And with the dysfluidic trials having a greater amplitude. And so this is the ERSP, and note that the condition type changes with the ERSP. So previously we had the word go, meaning that they prepared their speech, but now we have the Q word condition. And this subject 1, showed significance in the alpha and the beta, with both having power reductions, power desynchronizations, which kind of indicates that their brain is working harder. And also, I wanted to note that you can see that the dysfluidic trials have a less of a distribution. It's more flat across, as opposed to the fluid trials, which is a little more, in some areas it's higher activity, and in other areas it's lower. And we see a similar thing with the second subject, but only with the alpha frequency. And unfortunately, our third subject did not have any significant data for any trials or any of the things we chose, which means that maybe not every stuttering individual can have success with this experiment, which is also something really important to know. So just to summarize, as I said, I'm not trying to compare and make general conclusions, but I do want to kind of discuss the background behind why we're seeing some of these cues. So we had greater success with the ERSP, meaning that broader analysis signal. So maybe that broader analysis is better than having a time-locked probe wave response as we have in ERP. And then we also had greater success with the non-auditory condition, meaning that evoking the auditory cortex is maybe not necessary. Maybe there isn't as great as a role with the auditory cortex. We also had greater success with the Q word, meaning that the more realistic speech preparation setup was more beneficial for our classification of stuttering and fluid speech. And finally, we had greater success with the alpha frequency. And previous research has suggested that the alpha frequency desynchronizations, those alpha band reductions in the ERSP, that colorful map, those reflect the person who stutters over-reliance on the feedback mechanisms, because they're, as I mentioned way back, people who stutter are said to have disruptions with the feed-forward mechanism from motor to sensory areas, so they rely heavily on feedback mechanisms from sensory and motor areas. So in conclusion, we did find that there are distinct neural indicators that differentiate fluid and dysfluid speech prior to talking. But these results state in the success of this experiment, it differed from one subject to another, and also from one condition to another condition. And it may not work on all subjects, and we can't say that these features will be apparent in every subject. And just kind of why this is important is the next step in my lab is that we're trying to see if we can predict stuttering in real time. So as they're speaking, we'll be able to say, you're going to stutter, let's try to adjust your mental state, and that's like a new revolutionary way of improving speech therapies that is really awesome. So thanks for listening.